Oh yeah, timed hits, baby. Look at that. Yeah. Woo. Yeah. Uh-oh. Yeah. There we go. Take it. Yeah. Time defense, too. Look at that. Oh, who's a god gamer? That's right. Look at this. Oh my god. That's timing. Yes. Oh, look at that. 2 cycle. I mean, you know, this is clearly a speed run. Hell yeah. Oh no. What the crap is this? This is not Bowser. What sort of enemy is, like, a giant sword? Come on. That can't be real. It must be like a robotic mech factory that produces enemies or something. Spoilers? Alright, hello, hello, hello. Good afternoon, Internet. Welcome. Welcome to another NLMathman math help stream. Let me make sure my audio levels are all coming through correctly. Good. Good, look at that. Look at that. Why in the world, now, why in the world do we think? Why in the world do we think that Peter's on here playing a video game today? Well, because he doesn't want to do any math, yes. I mean, that's a big part of it, for sure. Right? But, I mean, what's this game offer aside from this rockin' tune, right? But, I gotta tell you, what in the world does this game offer? This links to the first topic that I'm going to talk about today, by the way, actually. Right? So now, instead of doing banter about, like, I don't know, pictures of me going hiking or something like that, today we're going to talk about this wonderful video game, this Super Mario RPG, Legend of the Seven Stars, for the Super Nintendo Entertainment System, published in 1995. Right? But most importantly, look at, see the directions I'm going in? You see the directions that Mario's moving around here, zipping around, jumping. I believe is there a hidden item over here somewhere? There is somewhere in this house that I'm forgetting about. Oh, is it on top of the lamp, I think? Let me try. Let me see, is it, no, there's a way to get on top of the lamp, isn't there? I don't know. There is something here in the Mario's house. Maybe someone who's more familiar with this game than I can tell me where exactly I'm... Oh, there's a secret, look at that. I mean, sort of a secret, an Easter egg, I guess. You get to rest like that. Mario blows bubbles out of his nose while he's sleeping. Right, one reason I want to show this on screen today before I get into my topics for today is because this game is actually an isometric game, right? You see up above me here, right? The topics for today include isometric drawings. I put the topics behind my head so I had enough room for today so you can see the game. We're going to do isometric drawing, we're going to do geometric transformations, Pythagorean theorem, and simplifying radicals, right? Whoa, okay, we're back. But one reason I wanted to show Mario RPG here is because this game is an isometric game, right? It is created in sort of a three-quarter overhead view, what was sometimes called at the time, but it's isometric in the sense that it's top-down. It's on an angle, sort of facing down at the game, right? And just to show you what that means, I'm just going to carry on here. I'm going to move in through some of the next zones. Oh, yeah, actually, I've just started the game, so I believe I had to talk to Toad here, don't I? Yeah, I think I had to talk to Toad, and then blah, blah, blah. Then some nonsense happens. Some story stuff. Whatever. Like, I'm not here for the story. Come on. Right? But the point is, when we look down at this game we're actually looking at it from a three-quarter sort of overhead view, right? We're not looking totally down on top of Mario. So, like, this direction and this direction. See, what I'm moving in is kind of diagonal, but those are basically the cardinal directions, sort of, in a game like this, right? Because you notice how down here in the corner, for example, how everything's sort of on a diagonal angle? That's because it's isometric, right? Which means it's sort of looking at something overhead at sort of a three-quarter angle, right? We're not looking at it head-on. And that's going to be super important for now when we get on to isometric drawing, which is the first topic I'm going to talk about today. So, Esther, that's going to be a topic for your courses, right? And, yeah, we're going to see that basically the sort of three-quarter overhead view kind of summarizes, I guess, what it is that we're looking at when we're looking at an isometric drawing on a piece of paper, right? Okay, so let me, okay, so as much as I love that rockin' music, let's maybe minimize that. Oh, I need to get my keyboard out of here. Okay, so then for today, I'm gonna get on and start talking. Oh, do I still have? Oh, okay. Mutarino, that one? There we go, Mutarino Cappuccino, got there. Okay, so over here on the side, this is an example of an isometric drawing, but it's, you know, it's set up sort of the same way that the blocks are, say, in the Mario RPG game that we were just looking at. I'm actually going to bring up another scene in Mario RPG here now in a second, so we can see a bit more clearly what I was talking about. But basically, what it is that when we're looking at something like what we see there over to the right, which is, Esther, one of the questions for your course, we see that we're kind of looking at the blocks from the corner. We're not really looking at it from the top, right? But we're looking at it more from the corner. And we'll see, yeah, let's skip back over to the game for a quick second here, just so I can show you another scene there. So if we look at this one, right, this one, it might be a bit clearer what's going on when I'm moving around in this. This is a later part of Mario RPG, right? I'm approaching a boss fight here now, so we're not going to go do that right this second. But if you notice, look at the blocks, right? The blocks that Mario's jumping on right now. You see those? You see how they're made sort of, we're looking at them from the corner, like it's got these J's on the side and stuff. Or that save block, that one down below me that's moving up and down. We see that we're looking at it sort of corner on, right? And if I was to jump, right, to get up, whoop, get up over that way, get up over that way. Oh, I'm going up. This is the wrong direction now. But we can see as I move through these areas, right, that I'm always moving sort of on an angle, but more to the point, the blocks that we see there, right, like right in front of Mario in this shot, those are very similar to the way that we're going to see the blocks in something like what we're looking at in the course over here, which is to say, like these ones, right? So that's just a short, a little bit of an illustration, I guess, on how isometric drawing and stuff represents 3D space, kind of, right? So let me just close that part down. So now I'm going to get into talking about the isometric drawings, and right now I have achieved printing power, right? I am now able to print again because I got a black ink cartridge courtesy of Walmart. I mean, not really courtesy of them. I mean, I paid them obviously. But I'm going to zoom in a bit with my camera here, and now I'm going to take a look at basically how we go about drawing these things in isometric sort of representations of 3D space, basically. So over here on the side, it says, now we're going to enlarge the shape by a factor of 2. Yeah, so Wild NLMathman appears. That's right. Yes. Yeah, maybe I'll show Pokemon at some point. That'd be fun. I don't know what way I could wrap Pokemon into it. Maybe the chance of like finding them in the tall grass. That could be good. I could easily show something like I don't know, Slay the Spire. That'd be fun. Anyway, so from here over to here, I'm going to basically take every single measurement on this shape, which is like looking down at a flight of stairs from the corner, right? Because these look very similar to some of the blocks that we just saw in Mario RPG, right? But I'm going to take this and just put it over here and make it twice as big. Now, the easiest way to do that is sort of to start at one point on the shape in the corner, just some spot, and then from that location, sort of make every measurement twice as long as what it was previously. I received the whisper you sent me earlier today. Sorry, I've been a little bit. Oh, I got it now. Yeah, I see it. Okay, yeah, great. Free open source algebra textbook that your students could find useful. Excellent. Well, thank you very much. Yes, I didn't see that this morning. I'm yeah, I was quite swamped. Well, not swamped, but I mean I'm always busy in the morning. But yeah, I will take a look at that after the stream is over. Maybe I'll send that out. Thanks very much. What I'm going to do for these shapes, right, is I'm just going to start at one point. Say I'm going to start at the corner, and I'm going to let it be, say here, just to hopefully have enough space, right? But so I'm going to start there, and I'm going to do this downward line first. Actually, am I going to have enough space? No, I might not have enough space. Maybe I'll tell you what. I will start here instead. I'll start there. And we see that currently, as it's written like this, right? It goes down 1, 2, 3 blocks. So, because I'm enlarging it by a factor of 2, that just means I'm going to double all the measurements. So I'm going to go down 6 blocks. So 1, 2, 3, 4, 5, 6. There we go. Right? And now I'm going to keep drawing sort of from this one, right? And as we see here, these come out sort of to the bottom right. And a common mistake that students make is to draw straight across on these blocks. But remember what we saw in the game, right? The blocks are not front on. They're sort of turned on the corner. So we're actually looking at the blocks from the corner, not from the front, right? So we're not actually going to draw straight across. We're not going to draw straight across like this. We're going to keep on these angles. So you multiply each length by the factor. Exactly. Yes. Each length in the shape is going to be multiplied by the scale factor. Right? So originally it was 1, 2, 3 blocks across the bottom. So now it's going to be, of course, 6. So 1, 2, 3, 4, 5, 6. There we go. Right? And now this is a little bit painstaking because I've got to do out every single one of these steps. But as you'll see, all I'm doing is doubling each length. So like from there to there was originally 1. So guess what? On mine, it's going to be 2, right? That's not hard. But the hard part is visualizing exactly where we're going to draw these guys. But if you do it, I understand that sometimes like it's difficult to have sort of the spatial awareness necessarily to be able to envision what the shape is going to look like before you start drawing it. I totally get that. But the way around that then is to just take it one line at a time. Basically, for each individual line you're drawing, look back at the original shape and say, well, is this new line that I'm drawing just exactly double what a previous one would be, right? So say I was looking at this point here, which corresponds to this one. There's a line that goes up, and it goes up 1. So now the line I draw is going to go up by 2, right? Same with over here. This one's going to go up by 2, then across there like so, right? And I'm just gonna keep repeating the same thing. Now the order in which I draw these sides, like the side that I start from, is really not super important, right? Well, all that's important is that whenever I get to a vertex, I make sure to draw my new line sort of in the same direction that the old one did, but multiplied by a scale factor. So here my scale factor is 2, so I'm just doubling every single measurement. If your scale factor was a half, you would take a half of every measurement. If it was 3, you would triple every measurement, right? Like, there we go. So, enlarge this shape by a scale factor of 2. There, we've got it, right? And that's a series of steps that we could see Mario jumping up. That was very similar to what I showed inside the boat there in that the scene from the game, right? So I have a few more that I'm going to get to, Esther, for your courses. I know that you wanted me to go over a bit about isometric drawing, so this is not going to be the last one. I've got a few others, right? So let's bring up the review sheet. I'm going to do quite a few questions from your review sheet. Need to see if I have any triangle rulers lying about. Yeah, triangle rulers are useful for sure, right? I mean, they're mostly I use this one mostly just as a straight edge, but it's also got this handy right angle stencil in the center, right? So if I want to draw a right angle triangle really quick, I just put it down and go boom, right, with the stencil, and then you've got one that you can use for a diagram or whatever. Right? Let me switch over. This is the review sheet here over on the side. So actually, let me change my scene over to this one because this one gets me a bit more space to show what I'm doing, because I don't really need to show the worksheet as much, especially for these types of questions. Right, but there's our original over there in the corner. Right? And now we're reducing the figure by a factor of 0.5. Now, what does that mean? Well, reducing a figure by a factor of 0.5 just means that the shape that we draw is going to be half the size of this one. Now, they were kind to you on this one in that I think all of these measures are, yeah, we're dividing all the lengths by half. That's right. So 1, 2, 3, 4, 5, 6. Yeah, I believe all these measures are even lengths, so we're actually going to still be on a whole number of blocks, which is nice. You can draw them like half blocks and stuff like that, but that gets a lot trickier. And generally, it's quite a bit easier to start off with doing it by whole blocks at a time. But anyway, I'm going to start at this corner over here, or what was this corner, and I'm going to do that down here. Right? So previously it went up by 2 blocks. I'm going to go up by 1. Right? And then we have a block on the end that was previously 2 by 2. So we see now it's going to be 1 by 1. Right? Just like that. So now it goes 4 this way. So now I'm going to go 2 this way, 2 that way. Let's see, 2 there, and also 2 there, like so. Join that one up. Okay. We noticed that this block here, this one was 2 blocks, or 2 dots rather, in from this end. So now it's going to be 1 dot in from this end, then it's going to go up. And this one went up by 1, 2, 3, 4. So we're going to go up by 2. Like so. 2 up there like that. This one from this corner went over by 2, so we're going to go over by 1. Right? I think you're probably seeing where I'm going with this one now. Check out and see what this length is. 1, 2, 3, 4, 5, 6. All right, so I'm going to do 1, 2, 3, like so. Hey, look, it's all meeting up. And if when you do it, now I wouldn't recommend doing it in pen like I'm doing. I'm doing it in pen because I'm ballsy. No, I'm doing it in pen because I want it to show up better on the stream. If I was modeling good behavior for these, I would be doing it in pencil just to show that, it's easy to make a small mistake on this. And as soon as you make one small mistake, the rest of your shape can go right out the window, right? So do it in pencil generally, and then you can erase little parts of it. But that's just how we're going to go about drawing these ones, right? So we're basically just copying it from over here, but now each measure is half of what it was before, right? So that's all we've got to do for that one, for that review sheet. Yeah, there were some other topics on the review sheet for me to get to. Let's see here. They're not all isometric, unfortunately, so we're done with our isometric ones right now. I do have the rest of the worksheet here, though, so I am going to go on and do a few more of these ones. Now, enlarging a figure over here, drawing the figure in pen because you know what the examiner is looking for. Yeah, exactly. It is important. It is important to know what your teacher is looking for. Absolutely, it is, especially in English courses and arts courses and stuff, because like every teacher wants your essays to be a little bit different. And people say that there are some universal rules, kind of, but every teacher wants a little bit of a different angle. So enlarge the figure by a scale factor of 2. Now again, we're going to take all the measurements here and try to increase them by 2, right? Now, because I'm doing it in pen, I'm going to have to go ahead and I'm going to have to count from the start and see how many we've got in the biggest dimensions just so I can make sure that my shape is going to fit, right? Fit in the space that I've got over here. If you're doing it when you're doing it yourself, Esther, or whoever else is onto these courses, you're totally welcome to, instead of using this place, just use your own graph paper. That way you won't have the issue of like potentially running out of number of blocks, right? Because your graph paper can be a lot bigger than what you would need. But here it's 1, 2, 3, 4, 5, 6, 7, 8 across there. So mine's going to need to be 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wow. Okay. So it's going to be the entire way across, entire way from one side to the other across this full shape there, like so. It's a bit hard to see, but it might be a bit clearer once we're done here. I think STEM subjects are much easier to grade as the answers are less open to interpretation. Some of the time it is, yes, yes. But there is still quite a degree of subjectivity in STEM courses, especially in the correcting of it. Like, what do you give part marks for, right? Like, say in a math problem, if someone makes an arithmetic error early in the problem and it causes all their answers afterwards to be wrong, but all their working is right thereafter, do you give them like 4 out of 5 or do you give them 0 out of 5 because everything's wrong, right? I would say 4 out of 5, or even 4.5 out of 5, maybe. But that's still right. There's a lot of subjectivity in the correcting and the evaluating of STEM subjects for sure. Let's see here. So up is 1, 2, 3, 4, 5. So now I'm going to need to go 10 up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let me count that again. Sometimes it gets mesmerizing trying to count just like that. I'm going to do it outside the line a little bit here, just so it gets dark enough that we can see it, right? This one here is going to be 10 as well, up this side. Just really trying to make it dark enough to see. Then what I'm going to do, for these triangles, I'm going to treat these triangles kind of like a slope, right? Like a rise over run. We can see over here that to get from this point to this point, it goes down 2 blocks and right 4 blocks. So since I'm doubling all the measurements, instead of going down 2 and right 4, I'm going to go down 4 and right 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Right there. And I'm going to draw a dot there. Then I'm going to draw a line down between those guys. And it's going to be, and then it goes from this point on up to there. And assuming that I've done every other line correctly, I'm going to go from this one over to here, like so. Right? So there we go. Enlarge the figure by a scale factor of 2. Well, all we had to do was find each dimension of the shape and then double each of those. Right? Yeah, let's quickly go over the rest of these ones, I suppose. So plot the triangle ABCD, coordinates, right? So -4, 2. This is going to be a lot faster than before because I've got the printouts here. Oh, my pen is leaking a little. Hold on. I really don't want the smudge because the smudges will sort of block being able to see what I'm doing very well. Okay, so we've got -4, 2, 1, 4, and 3, -1. Okay, so here's our original shape. Now, I like colorful stuff because obviously my aesthetic was heavily influenced by games like Mario RPG that we saw at the start there with all its bright primary colors. Very appealing, right? It's good. It's good stuff. So I'm gonna break out some more primary colors for my pens. Use a green here. So now we're going to draw the image translated 4 up and 3 left. So all we got to do is take one of our original points, count 4 up, 1, 2, 3, 4, 3 left, 1, 2, 3, and that's A. 1, 2, 3, 4 up, 1, 2, 3 left, and that's B. I should call these A prime, B prime, and C prime. So 1, 2, 3, 4, 1, 2, 3. That's C prime in there, and there we go. Right? So these questions might seem, even doing these out on stream might seem like, yeah, I mean, that's obvious. And I just wanted to walk through it just to model sort of what these ones should look like, right? But it is mostly just painstakingly, making sure to get all the points plotted correctly is all it's all you're really doing. Right? For those ones. I mean, I think they're fine questions, but there's not a ton of, not a ton of workings required in questions like that, right? Oh, you see how much is dripping. Look, it's soaked through the page. Look at that. Uh, let's see. Reflect the arrow. I'm going to skip that one for right now. I'm going to do the draw the quadrilateral, and then I'm going to rotate it. Okay? So, Esther, I'm going to show you, like I mentioned before, how we rotate this one using the compass method. Because on the test, you mentioned you do have a compass, so I would like to see you doing the compass method, especially on the test when you have that one, right? Um, because the compass method will show me that you're able to rotate it to any degree, basically, right? If you use the shortcut method, the algebra one that I showed you, um, which is basically, the algebra one is delta x, delta y. So the difference in the x and the difference in the y between your point and the point that you're rotating it to, when it's 90 degrees, it becomes, what was it, negative delta y, comma, delta x, like so. And your book does show all the different shortcuts, but if you are using a shortcut, then I do want you to write out the rule for it, right? And not just to go ahead and use it. So I want you to show me that you're using the the algebra behind it, so that I know that you know the workings. But I think the best way to do it is going to be to use the compass method. So that's what I'm going to show. So I'm not going to show this one. I'm going to do compass. Okay. So now let's see. D, E, F, G with coordinates D is -5, -5. -5, -5 right there. Bing. And that's D. And then E is -2, -3. -2, 1, 2, 3, -3. We've got 1, -5. So that is F there. And then the last one, -2, -7. That is G. Okay. So we'll see that our shape is going to be this guy here. Do 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 do. Okay, so we're going to rotate the figure 270 degrees clockwise around the origin. Now there is a little way to cheat, kind of, and just to see what it's going to look like even before you do it, right? And I do recommend students do this in order to just sort of take a look at what it's going to be like. But take your pen. I've got one where I can put the point of it away, right? Take your pen and put it on your center of rotation, just like this. And hold it down. I've got some pressure pushed here. And then take your paper under it, and then rotate it. We're rotating it 270 degrees clockwise, right? So 270 degrees clockwise is 270 this way, right? But 270 that way is the same as 90 degrees the other way. But let's do it. So that's 90 degrees clockwise. That's 180 degrees clockwise. And now this one here is the 270 degrees clockwise. So that what we see, that gives us a preview of what our shape is going to look like. We know that it's going to be vertical, and it's going to be sort of moved over into this quadrant, right? We can see, because we see here now that it's in this, what is this, quadrant 4? Yeah, so it's in quadrant 4 now, whereas before it was in quadrant 3. But that's just a preview. That's just a way you can check and see what it's going to look like after you do that, right? I do want to see you using the method that we discussed, right? Which is, of course, the compass method. So I'm going to get my compass. I'm going to get my pencil. Peggy Hill has run out of pencils. No more pencils in reserve. It's a pretty dank meme. Boggle. Boggle? Anyway, nobody in chat gets that reference other than me. So, you know. With my Hank of the Hill references. Right? I think that was Hank of the Hill. So, what I'm going to do is I'm going to do like I did before, right? So I'm going to take my metal part. The metal part here, the part that doesn't write, that's going to go on the center of rotation. And I know that the center of rotation here, I'm told, is the origin, which is 0, 0. So the metal point is going to go on 0, 0. Then I'm going to take the lead, and I'm going to make sure that it's lined up. Let me turn it sideways so you can see it a bit better with my hands sort of being out of the way. So that's going to go in the center there, and this one is going to go on one of the points. So we can see there that I've lined it up with point F, right? And now I'm going to draw an arc, and I'm going to try to be as careful as I can not to put much pressure on my compass so that it stays roughly the same without moving in and out. Now, there's always going to be a little bit of error in these ones, and that's just human error, right? Because if you accidentally, say, put pressure on it and squeeze it even a tiny bit like that, see that tiny little bit? Something like that, that's going to be enough. That's going to be enough to put your answer off a little bit, right? But don't worry too much about it. There's always going to be some, right? Now I'm doing, like I said, 270 clockwise around the origin. Remember, 270 clockwise, like I said, is the same as 90 counterclockwise, right? So I'm going to rotate by 90. I'm going to rotate by 90 because my the protractor that I have, as we see here, this is a 180 degree protractor. Now you can get 360 degree protractors, but they're not as common, at least not around these parts. Most of the time we use these 180 degree ones, right? So if you've got one of these, you can't measure a 270 degree angle with this. But of course you can do 360 minus 270, which is 90. And then instead of doing 270 clockwise, we can do 90 counterclockwise or anti-clockwise, depending on who you are and where you're from. So I'm going to keep flipping my paper around to hopefully give you guys a bit of a better vantage point. But we see what I've done here is I've drawn a line now from the point that I'm rotating to the center of rotation, which is the origin. Now I need to make a 90 degree angle with this line that I've just drawn. So I'm going to take that and I'm going to put it here like this, right? We see now that the crosshair, sort of this bit here, is lined up with the point of rotation, and then this bottom line across there is lined up with the line that I've drawn. Put that there like that there like so. Now what I'm going to do is I'm going to find 90, and of course 90 is the same no matter which side I count from, obviously. And then I'm going to draw just a little notch out here, just to show myself what direction to draw my line in. So now I'm going to go back, and this little notch that I've drawn, and the center of rotation, I'm going to make sure to line those two up thusly, right, like so. I'm just using the bottom of my protractor now like a straight edge. Then I'm going to draw a line that connects those. Now, we're going to see, well, what's the point? What's the point at which this arc that I drew originally and this line that I've just drawn, where do they cross? Now, I see that it looks like I was a little bit off, but I can see that it's going to cross here at this point. Oh, I'm going to use green, aren't I? Yes. Going to use green for that one. So now, there was point F that we've rotated. So now we're going to go ahead and we're going to call this one F prime. F prime meaning a rotated point F, right? Now, like I said before, we can cheat a little bit to save ourselves a bit of time, and then to use our preview, and we see from our preview if we turn it like so, right? We see that F is now going to be the top point, E is going to be E and G are going to be say down 1, 2, 3, and left 2, down 3, left 2, down 3, right 2, right? So we can, by looking at this, see how our shape is going to be rearranged. But let's rotate at least one other point just to show you sort of a bit more about how it works, because sometimes it can be tricky to try to draw a shape like this, right? I've had students do it before where they would try to draw it and they would just draw the same sort of sideways diamond over here. Like point F would be rotated right, and then the other three wouldn't. So I can give, I don't know, like out of 2, I can give maybe half. Maybe 1 if I'm being really generous. I can give 1 out of 2 for that, but still it's hard, right? So I would recommend, let's rotate at least one other point, and we'll see how the shape starts matching up, right? Excuse me. So I'm going to rotate point G. I'm going to do the same thing as before. Pointy bit on the center of rotation, leady bit on the letter, right? Give you guys a bit of a better vantage point there, right? Like so. Now straighten her up and draw the arc. Right? It's never going to be perfect for an arc like this. Compasses, I mean, unless you got a compass that like screws into place or whatever, you can get some pretty serious ones that like have a screw kind of a thing up here, so that after you move it, you can tighten it up really tightly, like mechanically tightly, and then it's just not going to move. But for ones in the like the math kits that we have that we provide, or the ones that I would, if you're going to go buy a math kit, don't go crazy and go buy one like that, right? Just go to Dollarama or whatever. But anyway, so this is the arc for point G. Now remember our next step is to draw a line from point G to our center of rotation, which I'm going to do here, like so. Now we need to make a 90-degree angle, a 90-degree counterclockwise, or a 270-degree clockwise, which is the same, from that line. So I'm going to rearrange this again a bit. Just try to bear with me here. I'm going to line up the center of my protractor, and then line up one of the legs of the protractor with the line I drew. There we go. Center is on the point of rotation. The base of it is lined up with the line that I just drew. Now I'm going to go to 90 degrees, make a little notch here, like so. All right. Now I'm going to connect Reno. So there we go. There's that next line. So now I know that point G is going to be roughly, now it looks like it's going to be roughly around here. Now, one problem here with this activity, and it doesn't happen with the other activities, but it does happen with this one, right? And I'm just gonna show you real quick why there's a problem with this activity, right? Look at, you see, what's the measure there, right, of this block? We see that is about 1, 2, 3, about 4 millimeters, right? And what's this dimension? 5 millimeters, right? See, there's the problem. The person that made this document, and it's a PDF, but I guess by now I should have made a new one, right? I should have made one that fixed that. But these are not actually squares. These are rectangles. And the problem with drawing it on a rectangle like this is it's not, the new points you draw are not actually going to match up with the grid, right? You can still rotate it fine, right? But if you use the shortcut method like this one, you're actually not going to get it in sort of the real space location that it should be, and that's because the blocks are a bit skewed. Right? But I'm going to draw it there like so, and that's going to be G prime. Now on your test, it doesn't have that issue, right? But still, the rotation will still be done the same way, right? This is why yesterday I went and took it and drew it out myself instead of 1, 2, 3, half, 1, 2. So the other one's going to be here. That's why yesterday I went and drew it out myself instead of actually just printing it. Well, also because I didn't have didn't have a cartridge yesterday, so that makes it harder. It makes it harder to not have a print cartridge. That's for sure. So then another 3.5, 1/2. This is going to be D prime. But we'll see that once we rotate them all. Again, like I said, I'm just gonna skip a little bit and do E and D based off of the other points. But once we rotate our shape, it's going to be basically that. Now, again, to reiterate, one reason why the ones that I drew weren't actually on the grid exactly is because this is not a perfectly square grid, right? It's actually 5 millimeters by 4 millimeters for each of these squares. I guess because of some error that happened when the oh, this is probably what happened. Yes, sometimes these activities, these things were made to fit on legal paper, and they were resized to fit on letter paper. So that might be it. This might have been originally made to go on legal, and then once it got squeezed down to fit on a letter, that didn't get changed. Yeah, that's probably what it was. Anyway, the test has been fixed, and so the test doesn't have that problem anymore. But it's sort of a good, not really a good problem because it's still a problem, but it does allow me to know if you've rotated with the shortcut method, which is this one, or if you've rotated with the compass. Because if you rotate with the compass, you're going to get it on the spot that it's supposed to be. You're lost. Well, you're probably in your house in CBS. Would be my Holyrood. Never mind. That's rude. Um, okay, tell you what, Esther. How's about I show you one other rotation. And for this one, because of the error that I was just talking about, I'm going to draw this one out onto paper myself. Okay, so I'll do one more rotation one here now, and I'll do the question 8 from your sheet. All right, so I'm going to go on and do question 8, but like I said, I'm going to draw it out myself onto graph paper so that we're not having this error. Let me zoom out a bit. I got a bit. My dock cam gets a bit blurry zoomed in that far, but it's great, right? It's a great way to zoom it. I love it. I love it. I don't know if you guys haven't seen this for a while, right? You guys haven't seen this for a while, but I mean, look, like right, yeah, that's a good, yeah, it's a great, great. My little DIY boom cam. It's good stuff. Okay, there we go. So now I'm gonna draw this one out. So this is gonna be Math 3102C Unit 1. Okay, and one important thing for these questions is you need to be doing all the steps like I'm showing, right? And Esther, on the activity that you did the rotations, right? So I mean, you submitted answers to those questions, so you did them somehow, right? So the way that you did them got your answers roughly correct, right? But instead of doing it that way, I'm going to get you to do it with the compass method, right? So I'm going to redraw the shape that we have here, which is, let's see, it's -1, -2 for this one, and then it goes down 1 and 1 to there, and then down 2 to there, and down 2 to there. Right? Esther, if you can describe to me, say in chat maybe, the method that you use to rotate them, then I can use that to help teach you this other method, right? Because I mean, you did something because you got the questions done, right? But my concern is that there wasn't any workings listed, right? So I'm just wondering. I know it can be hard to explain, say, in the Twitch chat like that, but you can send me an email or something like that afterwards, right? To just let me know what is it that you've done to get these ones, and then maybe I can use that to help explain a bit better how we will go about using this other method, right? But now, so I'm going to rotate this 180 degrees about the origin. So rotate 180 degrees about origin, which is 0.00, right? Like so. I just spelled center two different ways in one sentence. Don't mind me. It's the way your tutor taught it to you. Okay, sure, but your tutor is going to need to follow along with the way that we're doing it, and your tutor is also going to need to show you how to get some workings down on paper, right? So the way that you've been doing it hasn't been getting it entirely right, and you haven't been showing any workings either, right? So whatever your tutor is doing to show you that, your tutor is going to need to show you how to show some evidence that of the working that you are doing, right? And that's the problem with a lot of tutors sometimes, is tutors aren't always teachers. Tutors sometimes are just like students who have done the course before and think, oh, I'll show this person how to do the work. But what they do is sometimes, now I'm not saying your tutor does, I've never met the person, right? But sometimes they'll just sort of show you how to get the answer and won't really show you how to do the workings, right? But you need to show the workings that you're doing. You can't just, oh, well, there's the shape. Well, I'm just going to draw a shape over here, and then we're done, and I'm going to move on, right? You have to show what you're doing in order to get to the answer, okay? And like I said, please um, look up left or right and up or down each corner from the point of rotation. I really don't understand what you mean there. Maybe you can send me an email afterwards with sort of a summary of the way that the tutor taught it to you. But what we're going to do is draw an arc, right? We're going to use a compass to draw an arc from the point that we're rotating, with the center being the center of rotation. So again, right? You get your compass, you set it up like so. This point goes on the center of rotation, which for us is the origin, or 0, 0, right here. And this point, the lead, that goes on the point of the shape that we are turning, right? So I'm going to rotate this top point first. So I'm going to take this part and put it here, take the lead and put it here, right? I'll straighten it up a little bit. There we go. And now I'm going to draw my arc. All right, so this is me drawing my arc. This is the first step here. So I'm going to start there, and I'm going to draw an arc that goes all the way around. I say an arc because it doesn't need to be a full circle, though you can indeed do a full circle. A full circle is totally fine. But I've drawn an arc now, and this is this first point here. Draw an arc from that point with the center on the center of rotation. So that's what I've done. Right? Point 2. Next, what we're going to do draw a line from your chosen point to the center of rotation. So I'm going to draw a line. Then my chosen point, remember, was the top one of the shape, this one here. So I'm going to, and my center of rotation was the center, or the 0, 0, the origin. So I'm going to draw my line here like so. Right? Now, step 3. Okay, draw an angle from the line in part 2 that matches the angle of rotation. What does that mean? Well, here it's 180 degrees, so we're not really going to see it very clearly here. But what I'm going to do now is I'm going to take my compass, right, my protractor, sorry, and I'm going to take the center point of the protractor, and I'm going to line it up there like so, right? So the crosshair, the part in the center, that's going to be on my center of rotation. This line, or the bottom line here, that one's going to match up with this line here that I've drawn, right? So it's going to match up like so. And now my angle is 180, and I know 180 is just a straight line, right? So I'm going to put it here like this. But the difference between this method and any sort of shortcut method is right now I can pick any angle I want. I can rotate this shape by 40 degrees. I can rotate this shape by 110 degrees. I can rotate the shape by 152.3 degrees, right? But the shortcut method, you can only do 90s, 180s, and 270s. That's it, right? So then your test is likely to give you ones that aren't right angles, right? That aren't necessarily 90, 180, or 270. So you do have to learn this method because the shortcut methods aren't able to do rotations of any degrees other than just 90, 180, and 270. Okay, so now that's the line that I've drawn. So that's my 180 degrees, which is, of course, as we know, just a straight line, right? So all I'm going to be doing is continuing the straight line out. And now, so part 4, there we go. So where this angle meets our arc, we draw the new point. So now the new point is going to be, well, again, I'm a little bit off just because of that. That's not because of the grid or anything like that. It's just because of me and the compass and squishing it together a little bit more than I should. But I know that the point is supposed to be here, and that's very close to what I got, right? So now to keep showing the rotation method, I'll do let's do another point or two from this shape, right? And then we'll just join them up afterwards. So let's say I pick this far corner down here. So again, our first step, line up our compass so that this is on the center and this is on the point. Right, so I'm going to put this on the center and this on the point over here. Right? Now I'm going to draw an arc that goes at least 180 degrees because I know 180 is the rotation that I'm going for. So I'm going to draw a fairly large arc here. Right? So this is my arc that I'm drawing, and this is why it's the compass method, right? Because we need this arc. Like so. Now, my next step, right? So that was part 1, right? Now part 2 and 3 I'm going to do at the same time here because, like I said, it's a straight line. Straight lines are 180 degrees. So I'm just going to draw a straight line or a 180-degree angle from this point through the center of rotation and then out through this arc on the other side. Right? So it's got to go through the point that I started with. So I'm going to line it up like that. Through the center, going to line it up like that. And then way out to the other side on over yonder. Sometimes it's tough to account for like the thickness of the lead and all that stuff as well. And now we see that our new point is going to be here where they cross, so our new point is going to be right there. Right? And like I mentioned before, if you want a preview of what it's going to look like, right? It's a little sneaky, but it's not really that sneaky, and it's a super useful thing to do. Just take your pen and put it on the center of rotation, and then just turn your paper. I'm going to turn my paper 180 degrees now, and then we're going to get a little preview of what the shape should look like when we're done. There we go. Right, so now it's going to be upside down with the point downwards. Right, you might have been able to visualize that, but hey, there's no reason to visualize it when you literally have all the tools you need to actually test it and find out right in front of yourself. Right, so I'm going to take ye old paper, rotate back. Right, but now I know that, say, the points are all going to be the same sort of distance apart as the previous ones were, and I've done 2 rotation ones now, so I think that's probably enough that I can go ahead and I can finish drawing out my shape. So my shape after I rotate it is going to be like this, right? So let me tell you what. Where's my pens gone? Let me color in this one, shade in this guy in black because that was the original, and I'm going to shade this guy in green because this was the new one, like so. So that was the previous point before the rotation. This is the point after the rotation, or the shape after the rotation, right? And these arcs are the things that I'm going to be looking for to let me know how you did the rotation, right? And then we translate the image 5 units to the right. Well, that's not hard now, is it? I mean, I'll do that just to finish the question, right? Because the question asks us to translate it 5 right. Well, translating 5 right is just taking these points and counting 5 to the right and drawing it again, right? 1, 2, 3, 4, 5. This point. 1, 2, 3, 4, 5. This point. 5 this one, 5 that one, and 5 right for that one. Right? That's all you got to do for those ones. Sliding into the right. There we go. I've slid E right. There we go. That's all. That's all you got to do to move those guys from side to side like so. Okay. Yes, Esther, I think hopefully that was a fairly good look at how we do those. Yeah, if you're still not sure what the way that we go about these, I am more than willing to give you some more sort of practice or some more videos on those, right? But let me know if you're still a bit confused about that, I will do up maybe something else for tomorrow to show this in a bit more detail here now, right? But I know it's tough to absorb this much information all at once, and we've been, you know, I don't want to give you too many hours of the same topic all at once, right? It's tough to absorb it. But I'll send you these notes shortly after the stream is done, and a link to the video, of course. So you'll be able to watch this one again. But yes, let me know if there's still any questions about that. And yeah, if you could just maybe summarize the way that your tutor has taught it to you, right? It's totally great for you to be using a tutor. That's a really good way of getting some extra help and some extra practice in. Just it's make sure that they're sort of showing it to you from the ground up, right? Because it's a common mistake that people who aren't teachers might make sometimes. Now I don't know, maybe he's a teacher, maybe he's a really good teacher, or she, I don't know, right? But sometimes my experience doing it myself as a student tutor is sometimes you kind of think, those teachers, they just show you all this other crap you don't actually need to know. I'll show you how to do it quick, right? And then in doing that, can I pass in the review again? Yes, of course, absolutely you can. Yes. You can, do that one and resubmit the full thing. Yes, please. Right? I believe I asked you to try some of the ones. Submit the whole thing again. It's totally fine. Absolutely. I am going to now. I don't really have an intro screen to pop over to. You know where you went wrong. Well, yeah, exactly. That's the point of these sheets, and that's one reason why I spend so much time going over the individual questions and sending you back these notes and these videos saying, oh well, here's one, and here's what the problem was, because the point of these is to target what you're having difficulty with, and then make sure that you can learn those before you go on and do your test or do your exams, right? So yeah, this is exactly working as intended. Right, so please do. Yeah, you can go back and redo those and submit it again. I would be very happy to see that again. Thank you. But this is not the exact page I wanted. But hold on here. Now I'm going to switch over to doing some radicals because Betty Ann asked for this one. And like I just was just about to say, I don't actually have an intro screen the same today because I've closed down the game. So it's just I don't have a scene of Mario RPG playing anymore. But yeah, before I get into radicals, I would like to talk about this page in your textbook, Betty Ann. So this is page 211. We see there down in the corner. And one nice thing about this textbook is it does have sections like this that do a really good job of explaining sort of the general rules that you're going to be using. Let me switch my background so we know that I've switched topic, switched background, right? So this is going to be Math 2101B, and this is Unit 1, I believe, but I'm just going to call it simplifying. Simplifying radicals. Right? I believe that's the topic for this unit. As we see here, when working with radicals, we've got several different rules that we need to know, right? And when I mentioned before that radicals kind of work like variables, this is one way in which they work like variables, right? Because we know that if we had, say, 4x plus 3x, that equals 7x, right? Like that's something that we've seen dozens, hundreds of times probably in the program so far. But by the same token, right, it works the same way with roots as well, right? They've shown here root of x and root of x, right? So we could call this, say, like root of 4 root of y plus, 6 root of y equals 10 root of y, right? And it's the same if we have actual values, excuse me, if it's the same if we have, digits under there as well, right? Like 2 root 3 plus, I don't know, 4 root 3 is going to equal 6 root 3, right? And like I said, you can use the following properties to help simplify. We know that they're commutative. Commutative basically just means that multiplication can go in either order, right? Commutative is a fancy way of saying reversible. The associative property, right? Yeah, that's just showing that the multiplication can happen in any order as well. Distributive and multiplicative identity. Yeah, multiplicative identity just means basically that we can multiply things by 1 by multiplying it by the same number on the top and the bottom of a fraction, right? These terms here, I'm not. Whoa, look at that. Looks like Zalgo stuff on the go. The will of Zalgo. Um, I'm not super concerned if you memorize these terms: commutative, associative, distributive, multiplicative, right? But you do need to know these rules. But these are ones that you probably are already aware of, right? And yesterday we were looking at restrictions on the variables, right? It is important to know when we have restrictions and why those restrictions arise, right? We can't take the square root of a negative, and we can't divide by 0. So remember earlier on, I believe we introduced non-permissible values. Yes, we did. Yes, I remember now for sure. I can't remember exactly which course it was, Betty Ann, but we did do non-permissible values in one of your earlier ones. And remember I said that most of the time, non-permissible values are when we're dividing by 0. But there is one other case, right? And the other case for non-permissible values is you can't take an even root of a negative number. This was another thing that I mentioned, right? You know how a lot of science and math courses are taught is that they'll kind of teach you one subject, and then eventually later on you'll do that same exact topic again, but it'll be done in more detail. Well, here's one example of that, right? So non-permissible values, divide by 0, but also even root of a negative. Now, the even root of a negative is a bit different than divide by 0, but it's not different in a way that you're going to need to know in this course. So I guess I could just stop talking there, but I'm not going to. There is an imaginary number called I. It's like a curly lowercase I, and that one is just a made up number, but it's the square root of -1, right? And in doing so, it allows us to open up sort of like another coordinate plane in sort of imaginary number mathematics that can run parallel to the natural number or the real number plane. But for this course, don't need to know that, right? So our non-permissible values are going to be dividing by 0 and even root of a negative, right? Because say the square root of -1 is undefined. But say the cube root of -1 is -1, right? And why is that? Well, because as soon as it's an odd root, like this, if we do -1 times -1, it becomes +1. Multiply it by -1 again, it's back to being a negative, right? So we can get the cubed root or the odd root of a negative, right? Cubed root or fifth root, seventh root, etc. But we can't get the even root of a negative. So then for these restrictions, right? So like for 1a, we can say x has to be, let's see, so that is to an even power. So their x could be all real numbers, right? Because a negative number raised to an even power is always going to be positive. So here, x is all real numbers, right? Um, for b, there, b it has an odd power on the x, right? And for example, say if we have a negative x squared is going to be positive, right? But a negative x cubed is going to be negative. And that's the sort of the same token, right? If we have a negative number raised to an even power, that becomes even, or positive, sorry. If we have a negative number raised to an odd power, that becomes negative. Or it stays negative, rather, I guess is a way of saying it. So for this one, we have x has to be greater than or equal to 0, right? Because we can take the square root of 0. Taking any root of 0 is fine, because 0 multiplied by, what number multiplies by itself 3 times to give you 0? Well, guess what? It's 0. What number multiplies by itself 10,000 times to give you 0? Still 0. Right? So then for C, I guess I should be writing out just to make these notes more complete, I'm going to write out the questions as well, so that when you're looking at these, you don't have to be flipping back to your book or whatever to see what the question was. For this next one then, x plus 3, root of x plus 3, and it's a square root, so we can't take the square root of a negative, but it's x plus 3, right? So if x is -3, -3 plus 3 is 0, we can take the square root of 0, it's totally fine. If x is -3.0001, then it doesn't work, right? So here we know that x has to be greater than or equal to -3. Because as soon as it's any bit smaller than -3, then this part doesn't work. Then for 1D, we have root of x over x. Well, here now we go back to the divide by 0 one, right? Normally x could be 0 because you can't take the square root of 0, but of course you can't divide by 0. So here we have x is greater than 0. Okay, I know you didn't ask for that one specifically, Betty Ann, but I did want to go over that really quickly, just to reiterate about the restrictions. Now, I believe, let me see here. I believe you asked me to specifically to mentioned page 212, number 4. Page 212, number 4. Hey, look at that. That is one that I had picked out to do as well. All right, great. So page 212, number 4, I'll do that one there now. So here we go. Let me flip over to my other display so we've got a bit more space, and zoom in a bit so you guys can see it on the screen. So let's do A and B first. Get a blue pen. Right, and this is page, yes, I should have wrote down the page. That was page 211. This is going to be page 212. So now for 4a, we have got 5x cubed times root x, all multiplied by root 2x cubed. Okay. These questions look way more difficult than they are, right? Because remember from before, remember another one of our properties, right? Like if we had root 2 times root 3, what does that make? Well, that makes root 6, right? And if you're ever confused, if you're ever on a test or some sort of high pressure situation where you can't go ask teacher if that works, just try it. Just try it in a calculator. Like, not too proud to admit that I did lots of this on tests in math courses, just because, like, why not, right? It lets you test and see if it works. So root 2 times root 3 is that, right? Root 6. Oh my God, look at that. It's the same, right? So there we go. We know now that's proof that we can check at any point when we have a calculator like this. And it doesn't have to be a TI-84, the calculator on your phone can do it too, right? So at any point we can check to remind ourselves that this is the case. But if it's the case here for a simple example like this, hey, guess what? The rule is going to work the same for this one. So what we're going to do is we're going to leave our part outside, just out there, just hanging out. 5x cubed is going to stay out here. And then this interior bit, these two are going to multiply together, and that's going to be inside our root. Well, there's the 2 is the only sort of coefficient there, so that one stays by itself. Then we've got an x to the 1 and an x to the 3. And we know that if we multiply numbers with the same base, we add the exponent, right? So this is x to the 1, this is x to the 3. That becomes x to the 4. And we know now what our square root of x to the 4 is, right? And this is one reason why I do recommend writing out the root as an exponent, right? Because it might not seem obvious to you at the start that the root of x to the 4 is x squared. But if we were to write our exponents as a fraction like that, which I do recommend, then all of a sudden, by knowing our exponent rules, we know that this is going to be 2 to the half and x to the 4 over 2, right? Because when we raise one exponent to another exponent, what we do is we multiply the exponents, right? X to the 4 over 2, well, what's 4 over 2? It's squared, isn't it? So we have 5x cubed, and this is going to be x squared. Then we still have our 2 to the power of a half. 2 to the power of a half, we can't evaluate, really, right? Because that's square root of 2, and to leave it as a radical, we just got to leave that guy alone. So it's going to be 5x to the 5. I'll put the 2 back under the root sign just to make it more similar to the way the book it shows it to you. But this was just sort of a long-winded way of showing you why, x to the 4 is root of x to the 4 is x squared. And it's because, because what this root actually is a fractional exponent. But the only rule that we really needed to know to resolve this guy was that if we have two roots and they multiply together, it's the same as the root of those numbers multiplied together. So let's check out a few more in question 4 then. Gonna leave it in blue here to let you still see that it's question 4. I mean -5 root x multiplied by 2 root 8x cubed, like so, right? So we're going to multiply the numbers out in front. Those ones are easy. -5 times 2, -10. Then we're going to multiply the ones inside. X times 8x cubed is going to be 8x to the 4. This is root of 8x to the 4. Now, here we've got a little bit more simplifying to do because we can break down some of this. We want to make our radical that's left over as simple as possible, right? So from the last question, I remember that the root of x to the 4 is x squared. So I can call that -10 x squared. I can take this one out. And then left in my root, right, I can start factoring out any perfect squares that I can get out of 8. And of course I know that 8 can be written as 4 times 2, right? Because 4 is a perfect square. 4 is, of course, 2 squared. Then I can call this -10 x squared times 2 times root 2, because the root of 4 is 2, right? So once this operation sort of applies to it, I can move it outside like so. This is now going to be -20 x squared times root 2. And again, right, that is simple. That's as simple as that guy is getting. Yeah, you asked for number 4, so let's do all of those. Just like I said before, right? Check answer to A. Did I mess up A somehow? Sorry, did I do something? Did I miss something on A? Doesn't look like it. Oh, is my answer to A different than what the book gives? That's odd. Five x. The book answer is 5x to the power of 2 root 2. No, I'm not understanding what you mean. 5x to the power of 2. 5x squared times root 2? Shouldn't be 5x squared times root 2, no. No, not unless that's supposed to be x to the negative 3, which it's not. No, I'll have to check and see what the book's answers give for that one, but I'm not seeing how my 4a is wrong there. Maybe it's been so long since I've done radicals that I'm just missing something so totally obvious. I'll have to check after. But I don't think that answer to 4a is wrong, right? Because the 5 is just going to stay outside. The x's are going to combine. It's going to be 2x to the power of 4. The root of x to the 4 is x squared. X squared times x to the 3 is x to the 5. Yeah, I'm really not seeing how that one is wrong, but I'm not saying it's not. I'm definitely not a perfect math student, that's for sure. But yeah, I'm not seeing how that guy is wrong. But if someone in chat has the reasoning for why I've messed up on that one, please do let me know. I am going to carry on with the rest of these there now. 5x squared. Yeah, they must have. Yeah, that sounds, Betty Ann. It sounds like the book is wrong for that one. To be perfectly honest, that's what it would be if this x cubed wasn't here, right? Like if this x cubed didn't exist, then it would be 5x squared root 2. But this one exists, right? So you've got to add them together because it's x cubed multiplied by x squared. Now, if that's what the book gives, and the book is just wrong for that one, it happens. It happens sometimes. Generally, it's generally I'm the one that's wrong if someone's wrong. But no, in this example, this one is definitely it was definitely correct from the way that the book is written. Yeah, that's definitely a cube there. That is an x cubed Dorino right there. You can't just vanish that guy. Anyway, negative 36 root of x cubed over 12 root of x, right? So negative 36 over 12, well, we can just resolve that right away, right? That's negative 3. That's not hard. And then we've got root of x cubed over root of x. So that's just root of x cubed over x, right? Which is negative 3 root of x squared, which is negative 3x. Sorted, right? That was easy. Right? Factoring quadratic expressions can be difficult at times. Yeah. Factoring is tough for sure. Yeah, it is one of the trickier ones because of all those weird little like shortcut rules and things. The Slayer Darth, I do find that breaking out it's a bit overlong sometimes, but breaking out the good old quadratic equation that sorts those out pretty well, right? Because it works. It works every time. Sometimes it takes a lot more effort, and sometimes you get your answer as a decimal and you didn't want a decimal, but at least you get it right, right? Or you can use Mathematica or a calculator or Wolfram Alpha or Desmos or you know. But teachers don't always want you to just say because Mathematica said so. 3 root x, and then 4 root x cubed divide by 6 root of x to the 4. Okay. Yeah, again, this one's quite a lot easier than it looks as well. That tends to be a trend here. Book you have gives some really good tips. Yeah, I am going to check out that book that you linked me there in the messages once we're done here today. Let's see, 12. So on the top here, we're going to combine these coefficients. So it's going to be 3 times 4 is 12. And these ones here, like we saw over there, right? We can go ahead and combine these. So this is now going to be root of x to the 4, right? And then this is going to be divided by 6. And this one here has root of x to the 4. Now I'm just going to resolve that. What is root of x to the 4? Well, that's just plain old x squared, right? Like, easy. 12 over 6 is, of course, 2. And again, root of x to the 4 is x squared over x squared. Guess what? Answer is 2. Oh, not that one. Another book you have? Oh, you got a lot of those. Hey. Oh, but yeah, I definitely will check out the one that you linked as well. Like if the second term of the quadratic expression is odd, the number of terms has to be a combination of odd and even. Okay, sure. Yeah, I'm not. Oh, you mean the like when you factorize it? Yeah, yeah. Yeah. So let's see, Betty Ann, what was the next question that you asked me to go on to here? I had number six flagged as one that I was going to do. Six flagged. um, yeah, let's do a little bit of number six here because number six is shows a little bit more complicated ones than the ones in number four. So let's do that. Let's see, this is Math 2101B still. Unit. What unit is this? Is this Unit 1 in that course? I think this is Unit 1. And this is still going to be page 212, and this is going to be question 6. Okay. So 6a, I'll do a and b out of 6 for sure. So now we've got root of 12x minus 5 root of 3x plus root of 27x. Factoring is one of those things you really had to practice. Yeah, absolutely it is. It is for sure. Yeah, the odd problem has you stumped. Yeah, that's pretty much my life when I'm doing factoring questions for sure. Yeah. But in like statistical analysis or any sort of like, mathematical application that you get into later on, rest assured that all the factoring is going to be done by a computer, if indeed you have to do any factoring, right? Because unlike in a math class, generally the expressions and the modeling that you get is not going to factor very neatly, so most of the shortcuts are like never going to work outside of textbook examples. So you just sort of stick that into Wolfram Alpha or something in Mathematica and click enter. Right, number 15, sure thing. Yep, I'll put number 15 on the list. Yes, I think this is the only other topic I wanted to get to today. There were a few questions for Evan, but I don't think he's really going to need those examples because he did really well on the later questions. So it might have just been like a small little slip up on those questions for the Pythagorean theorem ones. So I'll probably leave those ones for now. If he really needs them, maybe he can let me know. But right now, what I'm doing for these, as you notice, is I'm splitting them up into perfect squares here, and then whatever's left over, right? Because 27 is 9 times 3, 12 is 4 times 3. And we can only actually do anything with this question by virtue of the fact that these can change like so, right? Root of 4 is 2, so this is 2 root 3x minus 5 root 3x plus 3 root 3x. Just going to be negative. I already see what it's going to be, right? Isn't that funny? It's a big old 0, right? Because the only reason we can combine these guys is just like what we saw on the previous page, right? But just remind you of the rule here, right? So like, um, if I wrote it out in general, so say y root x plus z root x equals y plus z root x. I don't know. That's maybe writing out in this sort of general form is a little bit even more confusing. But say it was like 2 root x plus 3 root x equals 5 root x, right? That's just sort of what I'm saying. This is kind of the rule. It's a bit small to see on stream there. That's not super important. That's sort of the rule that I'm using here. But, all that's happening out of that is we are combining those parts in 6 together, and it comes up with a fat 0. 0 cases today. Good. It's another good 0. I like zeros. I like zeros for case numbers for sure. We've been doing really well for that. It is tragic to hear about that doctor in New Brunswick that has been the center of some spread. Although that's at 15 cases, I believe, in New Brunswick as a result of that one incident. Which, I mean, that's bad, but it could be a lot worse. Hopefully those numbers stay Hopefully that was nipped in the bud closely enough that 15 is as far as it goes. But, apparently there was some long-term care homes that it might have moved into because of that incident, right? So, I don't know. We'll have to see. Have to see how that goes. So now, I'm going to simplify this. Well, there's not a massive load that I can do to simplify this one, but I can take this term and multiply it by both terms inside there like so, right? And this is 2x squared times 2x squared, root 2x squared. So this is going to be root 2x squared plus 4x times root 2x, right? So it's just going to be, we can call this 2x plus 4x root 2x. Well, that's it. Like, that's all we can do for that one, really. Like, I don't know. It's it's a little bit strange to see a question here like this that we can do so little for simplifying, but I do want to show this as an example that sometimes there's not going to be a ton we can do. Now, we could take this and put it back under this root if we wanted to, but, and we could take this and put it under the root too. We could put it all under the same root, but it just tells us to simplify, right? So that is basically as simple as those questions are getting. What other ones did I want to do? Yes, you mentioned number 15. I will do number 15. Yes, I also wanted to do number 14. Number 14 and number 15, to my mind, are some pretty good questions on this topic. And I like number 14 because it brings up some other types of math, which I always like a little cross-curricular. Although it's not really cross-curricular if it's all math. Now, is it? Yeah, whatever. Just technicalities. But for number 14, I'll do that one. Then I'll do number 15. And that hopefully will be a decent look at this topic in general. So, at Trent's local mall, a circular water fountain is set inside a triangular prism as shown. Okay, so like so. This is what we call an inscribed circle, right? It mentions that here. Trent has learned that this inscribed circle is related to the sides of the supporting triangle by this formula, where R represents the radius of the inscribed circle in meters, S is half the perimeter of the triangle, and A, B, and C represent the lengths of the sides of the triangle. Wow, right? That is a good geometry formula right there. He would like to determine the radius of the fountain. Number 6B. Yeah, I guess the textbook maybe says something very different for 6B, does it? So Trent feels that he can divide each S in the numerator with the S in the denominator. Is he correct? And explain. Well, no, he can't. I mean, he sort of can, right? He can divide each of those S's by this S, yes. But then he has to divide each of these other terms by the S as well, right? So that's just, yeah, Betty Ann, I'll check 6B and see the way that the book has it written. The book might have combined some of these things together under, like, you could combine this under that root, and we could call this, say, 2x plus 16 is 32, 32x to the 3. We could call it that, right? We could even call it no, that's about all the we could call it that, right? There's I don't know. I will check that answer in the book in the back of the book and see what they say and get back to you later, probably on the next stream, maybe just to mention. For 4A, 14A, can he divide? No. Did you simplify it right from the start instead of just starting the way it was written in the book? Oh, did I write it down wrong, maybe? Oh. um, what did I do? That's not 6B. That wasn't question 6B at all, was it? What in the world did I write down? Oh, that was 8B. Oh, that was 8. That was 8B. Never mind. Never mind. All right, okay. That was 8B that I did. Okay. Sometimes the problem, sometimes the issue is a little simpler than what we had thought it to be, right? Tell you what, seeing you got it, seeing you had it opened up there, how about I do 6b really quick as well? Turns out I did 8b. These things happen, right? Yeah, so seeing you've got 6b there in front of you, let's do 6b as well. So that's going to be 2x root x times root x plus 4 root x to the 5. Okie dokie. All right. So now we're just going to take this and multiply it by both those terms in there, right? So when we multiply by the first term, the 2x on the outside is going to stay like it is. And on the inside, we're going to have root of x squared, right? Then for our next term, we're going to have the 4 multiplied by the 2x. That's going to become 8x. And then this root x and this root x to the 5 is going to become root of x to the 6. And now I know that root of x squared is x, so this is going to be 2x times x, 8x, and then root of x to the 6 is going to be x to the 3. So that's going to make 2x squared plus 8x to the 4. And that's probably as simple as they're bringing it. Or what we could call this is we could factor out the biggest term that we can out of both. And this could be called 2x squared outside of 1 plus 4x squared. We could call it that as well. Okay? Turns out, yeah, turns out I did 8b and not 6. But, you know, these things happen. So that, or that, I'm not sure what one the book would give you. I would imagine I would err on the side of giving that. But you could reasonably say that this is more simplified because we've now factored out the biggest term that we can. Actually, you know what? I was going to do question 14, but I guess I didn't really look at it closely enough. I'll tell you what. Question 14, I thought we were actually going to have to do some arithmetic with that wonderful formula when I glanced at it, but we don't actually. We just have to state the restrictions on it and stuff. So forget that one. That's silly. So let's indeed do number 15, like you mentioned, Betty Ann. 15 there. So our formula for number 15 is going to be 3 root 2 minus 2x. 3 root 2 plus 2x. Ah, look at that. Divide by 2 root of x. Okay, so what are the restrictions on this variable? Well, remember now, we can't take the square root of a negative, right? So we know that x here can't be negative. We also can't divide by 0. So the restriction is that x has to, oh, right, wrong one. X has got to be greater than 0. That's our restriction, right? Because if x is 0, then this is root of 0 is 0, of course. 2 times 0 is 0. We're dividing by 0, and then we cause a black hole, and no one wants to be the cause of a black hole, right? So we know that x has to be positive and a greater than 0, I mean. So then it asks us to simplify the expression. Let's go ahead and do the FOIL, right? FOIL this guy out. So our first one, 3 times 3 is going to be 9. Root 2 times root 2 is going to be just plain old 2. Right? So that's the first two multiplied together. Then the outer is going to be 3 times 2 is going to be 6. 6x, and then a root 2. This next one is going to be negative, because we see this is a negative. This is going to be minus 6x root 2. And then this last one is going to be negative 2x times positive 2x. It's going to be a minus 4x squared. Yeah, so look what happened here. Look at what is happening. Those ones there are going to cancel and go away. This is going to be 18, then it's going to be 18 minus 4x squared, right? Then we can simplify that one down to be 2 outside of 9 minus 2x squared or something like that, right? And that's, all right, it's still going to be my mistake. This is still over 2 root x, and this is still over, okay, boy, oh boy, 2 root x, like so. Right, so I can divide both the top and the bottom by 2. Let me carry on over here. And this is going to be 9 minus 2x squared divided by root of x. That then should be as simple as that one is getting. Oh, done goofed? No, Slayer Darth. No, but those are the best times, right? It's making a mistake in math means that you're learning it, right? I mean, that's what you're supposed to do. You're supposed to find out about your mistakes and then go, figure out that they're the correct way of doing it, right? That's how we go through the learning process. It's all very platonic and wonderful, right? When you're the teacher and you can, if you get stuff wrong, it's not really a problem, right? It's teacher getting stuff wrong. It's just, like I say, it's a teachable moment. You're not with it today, Peter. No, what did I make a mistake with there today? What was the other one? Not seeing what the not seeing what the mistakes are there today. To be honest, I mean, yeah, I did the wrong question up there. You times that by the denominator. Well, yeah, sure. Yep, yep. We can. Oh yeah, I guess that's true. I guess that's true. Yeah. When we want to, if you want to multiply it out to get rid of what's in the denominator, well, sure. Yep. You can multiply the top and the bottom by root x. That's true, right? To make the so the denominator doesn't have a radical in it anymore. That's true. Yep. So we can. Yeah, that's true. We could say that we can multiply this one then by root x over root x. That's true, right? And then we could make that into 9 root x minus 2x squared root x over x. Well, sure, right? To my mind, that doesn't make it any simpler though. Right? If you have some sort of concerns or some comments about the way that I'm doing these ones, you can, please do feel free to let me know. Right? But again, for example, like some of those other ones that you seem to think that I was doing incorrectly today, I absolutely was not. So I'm not entirely sure what the problem is here for these ones. But anyway, if you see some sort of issue with the way that I've gone through and done these, please do let me know. Otherwise, I think that this is probably going to be the end of it for today. Right? I hope that was sort of I don't know. Maybe we got there in the end. I'm not entirely sure what the issues seem to be about these ones. Um, yeah, it's entirely possible that the book just takes it and um, takes it to a different point for simplifying it. Anyway, I guess I'll have to flip to the answer key for this one, and then take a look down through and see how this is how these ones match up with what I've done here. The answers in the back are off at times. Yes, that's true. That's true. But I mean, it is always annoying when it is. I remember. I know for this one here, right? This one here was definitely like this is definitely the answer for that question. But yeah, these other ones, if there were any problems with this, I mean, I guess we could have taken it from the start and then maybe multiplied the top and the bottom by root x to sort of cancel out the radicals from the bottom, right? But and it should really still work out doing it this way as well. Anyway, um, yeah, I hope that's been it's been interesting and you know illuminating, entertaining, and various other qualities, right? But thanks for joining me there today. I'll have to go take a look at the answer key in the book and see if I need to brush up on this topic myself. But yeah, I'm not seeing what the mistakes are off the top of my head, but we'll definitely take a look at those ones to see. All right. Well, thanks for being here today. I hope to hear from you again tomorrow. Stay safe and yeah, keep working on some math, I guess. See you later.